We will continue our discussion of semiconductors and look into doping and diodes. Recall that we brought together the isolated atoms with their quantized energy levels, and that those energy levels formed bands, regions of allowed energy, and separated by gaps, regions in energy space that are not allowed. And then we filled up those bands with electrons in the lowest energy levels, and then the last filled energy level, the Fermi level, its position within a band determined whether the substance was a semiconductor or a metal or an insulator. Next, we want to consider the effect of doping, sort of sprinkling in some atoms that are nearby the semiconductor in the periodic table. Let's try to understand the effect of doping using an analogy. So let's imagine a university that offers 100 level courses, 200 level courses, 300 level courses, etc. These courses are going to correspond to our bands. And so the 100 level courses are all of a similar difficulty. The bands were quasi-continuous, but the 200 level courses are significantly harder. There was a gap between the 100 and 200 level courses after all. And then we're going to fill up these bands, so we need to have some counting argument. So in our analogy, we're going to assume that the university offers 10 classes at each level, and then each class has a strict cap of 20 students in the course. So each level has an occupancy of 200, 10 classes times 20 students. The course levels again correspond to the bands, and the change in the difficulty level between a 100 and a 200, that corresponds to a gap. So at what I'm calling the Semiconductor University, the students take 4 courses. This is analogous to silicon having 4 valence electrons. So say we have 100 students at the university, and they must take then 400 courses, each of 100 students taking 4 courses. So the students at Semiconductor U are going to register for their courses, and they're going to, because they're smart or lazy, depending on your point of view, take the easiest courses. But those courses will fill up. So remember, we have 100 students taking 4 classes, so 400 slots to be filled, and then the 100 level had itself 200 slots, and the 200 had 200 slots, and so that's where we end up. So we are making, by taking the lowest, the easiest courses, filling in the lowest levels, we are making what's called the ground state. And then that last course filled is analogous to what's known as the Fermi level. So when registration occurred, the students took the easiest courses, and all the 100 levels were filled up, and all the 200 levels were filled up, and that's where it ended. And then the next available course is in the 300 levels. So we were at the gap. So we were equivalent, analogous to a semiconductor, and so that's why I'm calling it the Semiconductor University. Now we want to talk about why semiconductor is not a good conductor. Why doesn't it conduct? So if we want to conduct, we want to induce a current. So our analogy here is going to be to have some kind of flexibility. So there's an afternoon job, and a student wants to take that afternoon job, but has to change their schedule. They have some scheduling conflict to be able to take this job. But now, to change your schedule, to get the flexibility to take the afternoon job, you have to take a much harder course. That student is going to have to take a 300 level course. So first of all, the students down in the 100 level courses aren't even going to think about it, but even the ones in the 200 level course have to sort of think about it. Even the ones in the harder 200 level courses have to think about it, because the 300 level courses are significantly more difficult. So the schedule flexibility is like conductivity, or the lack thereof, because the inflexibility of the schedule is like the reluctance to conduct. And so we have this pure semiconductor, and it does not conduct very well, because this need to jump the gap in order to give you any flexibility. Now let's say this program introduces an exchange program. So some percentage of its 100 students belong to this exchange program, and those exchange students are only taking 3 courses. In this case, then, not all the 200 level courses would have filled. And so then the afternoon job becomes available and some student needs some flexibility in order to take the job. Well, if that student is in one of the higher 200 level courses, but not the highest, that student's going to have to take just a slightly more difficult course to get the flexibility to have the afternoon job. So there's, in this situation with the exchange program, there is more flexibility because not all of the 200 level courses filled. And so there's more flexibility or higher conductivity, and this is analogous to p-doping. Next, let's consider a different type of special program. In this case, it's a 3-year program. So we have a percentage again of our 100 students who belong to a 3-year program, and those in the 3-year program are going to take an extra course. They're going to take 5 courses a semester. So in this case, then we have more than 400 slots being occupied, and so there are some students already taking courses at the 300 level. So the afternoon job becomes available, and if it was a student already in a 300 level course, then that student can take the afternoon job without having to take a significantly harder course, just a different 300 level course. Slightly harder, but not much harder. Again, quasi-continuous. And so again, with this 3-year program, we have, again, more flexibility, higher conductivity, and this is analogous to n-doping. So we see that doping improves conductivity. In our analogy, we saw that if we have some fraction of students taking fewer courses, it improved the flexibility, the ability to take the afternoon job. That was p-doping. Similarly, if a fraction of students took more courses, that also improved flexibility, and that was n-doping. So either type of doping improves conductivity. But there's got to be more to it than that, because if all we wanted was a better conductivity, then we would just start with something that was a good conductor to start off with. So there must be more to it. So we can change the conductivity a bit. So what? The interesting stuff happens when we bring a p-doped semiconductor and sort of join it with an n-doped semiconductor. This is known as a p-n junction. So let us push our analogy a little further. So to make a p-n junction, we need to bring p-doped and n-doped next to each other. So let's imagine we have a city with 2 universities. There's the p-doped university. It has the exchange program with the students taking fewer courses. And then there's the n-doped university, and it has the 3-year program, so it has students taking some extra classes. So some students at NU, the n-doped university, who are up in the 300 level courses, they have a friend over at PU, and the friend at PU tells them that there's some open slots in the 200 level courses. So of course, some of the students taking 300 level courses at NU want to take their courses over at PU and take a 200 level course instead. What does this mean in the non-analogy? It means that there are unoccupied low energy levels in the p-doped material. So when the students taking 300 level courses at NU decide to take 200 level courses over at PU, there's some penalty. Maybe they have to pay some extra fee, or maybe it's only good for students who live between the 2 universities, and for other of the 300 level taking NU students, it will result in a longer commute, but there's some penalty. Let's get out of the analogy for a second. What's the penalty in the real materials? It's charge separation. So before anything happened, when we had n-doped and p-doped materials separately, each one of those is electrically neutral. So we might think of there as being extra electrons in the n-doped, but those extra electrons floating around also came with the corresponding nuclei that had extra positive charges. And so it was neutral. Same thing for the p-doped. We might think of there as being fewer electrons, but it's not really fewer electrons, but fewer free electrons. And that condition of fewer free electrons came with a reduced positive charge than corresponding. So everything was neutral. The n-doped material was neutral. The p-doped material is neutral. But when we bring them together, and some of the electrons in the n-doped material go over to occupy lower energy levels in the p-doped material, now we're getting some charge separation. One will be have a net negative charge, and the other side will have a net positive charge. And charge separation costs energy. Let's talk about capacitors or batteries. When we charged a capacitor, we ended up with a separation of charges, and that cost energy. When you charge a battery, it's similar. There's some arrangement of charges, and to charge the battery, you have to give the energy to get that arrangement of the charges. So there are certain charge arrangements or charge separations that cost energy. So let's say that we used phosphorus to dope silicon. Well, phosphorus may have one more valence electron than silicon, but it also has a nuclei that has one more positive charge. So these two compensate each other, and so the phosphorus doped silicon would be neutral. Similarly, if we did aluminum doping of silicon, the aluminum may have fewer valence electrons than silicon, but it also has nuclei with fewer positive charges. So again, aluminum doped silicon would be neutral. It's when we bring them together, and the phosphorus doped and the aluminum doped silicon, if we were to bring them together and some of the electrons from the phosphorus doped side went over to the aluminum side, it's then that we would get a real charge separation. We would be violating charge neutrality, if you will, that at least on a small scale, that one side would get a net charge and the other side would get a net charge of the opposite sign. So the n-doped had some charges in a higher energy state, and they saw a nearby lower energy state. That's a bit like a battery that wants to get to the lower state, but it causes some charge separation, and so we end up with a net negative charge on the p-dope side and a net positive charge on the n-dope side, and so that's a bit like a capacitor. So it's a bit like we had a battery charging a capacitor, and at some point it comes to an equilibrium when there's as much push from the capacitor as there was from the battery. But this seems crazy. There's now a loss in the flexibility. So we had, back to our analogy, some of the NU students taking the PU classes. Now we've lost the flexibility in the schedule. We got flexibility either in NU by having some students up in the 300 level courses, or we had some flexibility in the PU university by having some empty slots in the 200 level courses, and now the NU students are filling those classes over at PU, and so we've lost our flexibility, we've lost our conductivity. So we doped in order to improve the conductivity, but then we brought P and N together in a P-N junction, and we've lost the conductivity. So what have we gained? Let's attach a battery to our P-N junction, and let's have the positive side of the battery connected to the N-doped. So the battery pushes round charges, and it pushes them on to the N-doped side of the P-N junction. Well, there's already a bunch of positive charges on the N-doped side of the P-N junction, and these additional positive charges are just going to make a bad situation worse, and this is called reversed bias. So we have this problem of poor conductivity at that junction, and these positive charges are just going to make it worse, make it even a worse conductor, and so we don't get current flow in this direction. This is known as reverse bias. But if we turn our battery around and now have the positive side of the battery connected to the p-doped, so the battery is sending out positive charges now into the p-doped side of the p-n junction, and the p-doped side is where we have the sort of net negative charge, then these positive charges are sort of relieving the situation, making that region of poor conductor smaller, and then allowing it to improve its conductivity. And this is a direction in which we will get some flow, and it's known as forward bias. This is a little oversimplified, but it's the basic idea. Thus, with a p-n junction, we get current flowing easily in one direction and poorly or not at all in the other direction. Devices that have this property are known as diodes. So basically, a p-n junction is a diode. It's got a similar function to like a valve in a heart. A valve in a heart lets blood flow in one direction but not in the other. In the lab, we will see some uses of diodes. Some diodes can be configured so that when electrons cross the junction, the p-n junction, they will give off a photon, that is light, and so they glow when they are conducting. And this makes them light-emitting diodes, or LEDs, and they can be used to make simple displays. What are called organic LEDs, or OLEDs, can be used to make more sophisticated displays and are becoming an alternative to liquid crystal displays. In a way, the reverse situation to an LED, which is giving off a photon, is the photoconductor. So an electron that is at a gap may be given the extra energy it needs to get into the conduction band, to jump the gap. It may get that energy from absorbing a photon of light, so that the energy of the photon becomes the electron's energy, and then it can move from the valence band into the conduction band. And once in the conduction band, it is free to move. So you get something that when there is light around to promote the electron into the conduction band, you get conductivity, you get freedom of motion, you get an easy current. And so then you have something that will conduct in the presence of light, and thus it is something that can detect light. And then if it's detecting visible light, then we would call it a photoconductor. It conducts when there is when there is light. In a photoconductor, the presence of light, the photons, help promote the electrons from the valence band up into the conduction band, and so they are poor conductors in the dark and reasonable conductors in the light. That makes them light detectors, because we can detect this difference in conductivity, and that makes them a key technology, photoconductors that is, in photocopiers, lasers, printers, scanners, digital cameras, anytime we are trying to detect light.